Okay, our next format, our next speaker is remote, and he actually recorded his presentation, which is very helpful but kind of unique to what we're doing today. Everybody's kind of in a live body. He's been trying to call in. He's in Ithaca, New York, and I believe he talks about himself here a little bit at the beginning, but he couldn't be here in person, but wanted to make sure that we had his presentation, and again, went through it verbally with a overlay of his presentation. He's trying to jump in online, but somehow his, I guess Cornell is, they have a Big Brother lockdown as far as internet goes, and he's having a lot of trouble trying to get into our webinar. Hopefully you don't have too many questions, and hopefully everything flies well here, but we're going to go ahead and get started.
Thank you for the opportunity to speak with you today. I'm sorry I cannot be there in person. Next to last week of our semester at Cornell, and I'm simply unable to leave campus at the moment. Sounds like an exciting meeting you're having. It would be great to be there in person with you. Today I'd like to talk about the role of methane in the greenhouse gas footprint of natural gas generally, and shale gas in particular. I published the first ever peer-reviewed paper on this topic 4 years ago last week, and today I'd like to briefly summarize our paper and tell you about the incredible amount of additional science that's happened on the topic since then. Our paper came out in the spring of Our paper came out in the spring of 2011. At that time, the shale gas phenomenon was fairly new. This shows the trend in the United States, and almost all shale gas development has been in the United States. More than 2/3 of all shale gas ever developed has been developed since our paper was published. Now, the research question we undertook is natural gas a bridge fuel? Industry likes to promote natural gas as a bridge fuel. President Obama has bought into this concept, and in some ways it makes sense. If you look at the amount of carbon dioxide that's emitted to get a particular unit of energy, the emissions from natural gas are substantially less than from diesel or from coal. But that's just for carbon dioxide. The problem is that natural gas is mostly methane. Methane is an incredibly potent greenhouse gas, and even very small emissions of methane to the atmosphere can have a very large influence on its greenhouse gas footprint. This hadn't really been looked into before our paper came out 4 years ago. And this shows you some of the literature up until our paper and our estimates. These are estimates of methane emissions expressed as a percentage of the lifetime production of a gas well going to the atmosphere as methane. Full life cycle assessments all the way from the gas well to final consumer. Before our study, the EPA was saying there's about 1.1% of emissions. Department of Energy study by Hale et al. Had a substantially larger number. Yamarillo et al. Peer-reviewed paper that simply used the lower EPA number. Our number came out right on with the Department of Energy study, although that's surprising in a way because we use largely independent data sets. We also concluded that for shale gas, which no one had looked at before, the emissions are substantially larger than for conventional natural gas. This is the summary slide from our paper from 4 years ago. Let me talk you through the bottom right-hand panel there first, the 100-year time frame. What you're looking at is the greenhouse gas footprint of shale gas, conventional natural gas, coal, and for oil. And we're looking for both shale gas and conventional natural gas as our high and low estimates for methane emissions. So the blue bars are the direct emissions of carbon dioxide from burning and using the fuels. The red bars are the indirect carbon dioxide from obtaining the fuel, mining the coal or doing the high volume hydraulic fracturing, for instance. And the magenta bars are the methane emissions that are normalized to carbon dioxide equivalent. At this 100-year time frame, at our high estimates for methane emissions, particularly for shale gas, the greenhouse gas footprint is worse than that from coal or oil. For conventional natural gas, there's the low methane assumptions, then conventional natural gas has a lower footprint than coal or oil. However, the differences are not huge. And if we look at shorter time frames, the top panel here, the 20-year time frame, same idea, except now because methane has a more pronounced influence at these shorter time frames, even at relatively low levels of methane emission, shale gas in particular, but even conventional natural gas has a greenhouse gas footprint that is bigger than coal, larger than that of oil in many cases. The difference in the two time frames is simply that methane only hangs in the atmosphere for about 12 years. And so if you are averaging it from the time it's emitted over 20 years, it has a much larger influence than it does if you average that over a 100-year time period. I'll come back and talk about that some more in just a moment. Our paper got a huge amount of attention. We got cited in over 1,400 papers in the first 9 months, and Time magazine in their December Person of the Year recognized Tony Ingraffea and I as runners-up for the Person of the Year, based not necessarily because we're nice people, although I like to think we are, but because what we had done was newsworthy. It attracted a lot of attention and a lot of pushback from industry because of that. This is just to give you an example of other people who were runners-up for Person of the Year when we were, and you can see this isn't necessarily overall company you want to be in, although I do admire some of these people. At the top of the slide, you can see that both methane and carbon dioxide are important. Carbon dioxide is the largest causer of climate change according to the IPCC, with 1.66 watts per square meter of heat trapping. Methane is not that far behind at 1 watt per square meter, so it's an important greenhouse gas. Now, both methane and carbon dioxide are carbon-based gases. They are the two most important greenhouse gases, but they have some very important differences that I want to stress. For carbon dioxide, the emissions that we're putting into the atmosphere today will continue to influence our climate for thousands of years into the future. So it is critical that we do a better job of controlling and reducing carbon dioxide emissions. However, because of lags in the climate system, there's no immediate benefit of reducing the emissions. The climate will continue to warm at pretty much the same speed over the next 3 to 4 decades, no matter what we do with carbon dioxide. So we need to control it because of its long-term influence. Methane, on the other hand, only persists in the atmosphere for 12 years, and its long-term influence is quite modest, much less so than carbon dioxide, unless the warming that it causes in the shorter term leads to fundamental changes in the climate system. And there's increasing reasons to believe that that may be so. We're running increasing risk of that happening. And unlike carbon dioxide, if we were to reduce emissions of methane, it immediately slows the rate of global warming. On this slide, I'm showing you a variety of studies. These are listed chronologically by data publication. So the first 3 predated our paper from 4 years ago. Our paper came along, and then the rest of them here are a series of papers that came out in rapid succession in the 8 months or so after our paper. These are all addressing methane and natural gas. The ones after ours, it's largely looking at shale gas. No one had looked at it before, so it's sparked a lot of interest. The thing I want you to note here is that the studies in blue are looking at methane at both the shorter time scale and the century time scale, whereas the studies in black look only at the century time scale, which tends to underplay the importance of methane. And some of these studies are quite critical of us for also looking at the shorter time scale. In one case, the authors called us disingenuous for using a 20-year time scale as well as the century time scale because in their view it exaggerated the influence of methane. The Intergovernmental Panel on Climate Change, again in their report from 2 years ago, weighed in on this. They said that there's no scientific argument for selecting 100 years compared to other time frames, and that the choice of the time horizon should be based on the question at hand, the concern at hand. The IPCC themselves used a 10-year time frame as well as a 20-year and 100-year time frame. So there's plenty of precedent supporting our use of the shorter time frame. And since our paper came out, I've grown increasingly to think that the shorter time frame is the most appropriate one, the most critical one for policy versions. And that's based on this paper, which was published in January of the year after our paper came out, January 2012, paper by Drew Shindell et al., who was at NASA at that time. What they show is the rate of global warming over the 20th century up till 2011. We see a 7/10 or an 8/10 of a degree warming over the early 20th century baseline here. And then they have 4 scenarios running into the future. The yellow bar there shows the 1.5 degree temperature, and the red you get into 2 degree temperature. There are many reasons to think that these are dangerous temperatures. We run the risk of runaway feedbacks in the climate system, potentially if we start to reach those temperatures. Now, if we look at the scenarios, the green line there, the reference line, is what the trend we're on at the moment, and that is not doing much to control greenhouse gas emissions. And under this scenario, we'll hit that 1.5 degree temperature in 15 years, and in 35 years from now, we'll be at the 2 degrees threshold, very dangerous. The blue line marks CO2 measures there would be a prediction of what would happen if we were to aggressively control carbon dioxide emissions beginning back in 2011, which of course we haven't done. And because of lags in the climate change system, again, we will still reach that 1.5 degrees in 15 years. The short-term benefit of CO2 control is non-existent. The next line down, though, is if we were to ignore carbon dioxide, focus in on controlling methane, and also black carbon, abbreviated BC, which is soot, basically. And here, the climate warming immediately slows, still warms, but at nowhere near the rate. We buy ourselves considerable time before we hit dangerous temperatures. And of course, the ideal is the bottom line here, where we control methane, black carbon, and carbon dioxide. That's what we really need to do if we're serious about climate. Let's turn to looking at the methane emission estimates, and what this slide shows you is largely focused on what the Environmental Protection Agency has done. So I'm showing the Department of Energy estimates for conventional natural gas from 2002, our estimates, and then a few estimates from the Environmental Protection Agency over time. Here are separated into upstream emissions, that is at the well site or at the gas field, and downstream emissions that are happening from storage tanks, distribution pipelines, and long-distance transmission pipelines, as well as the total. If you look at the downstream emissions, I'll come back to this briefly later in my talk. The Department of Energy number and ours are identical again, although they're based on completely different data sets in this case, so that the agreement is truly coincidental. The Environmental Protection Agency number is lower, and it's based on some industry studies from the 1990s, which EPA has not yet updated at all. What they have updated, though, are their estimates for the upstream emissions. And what we're looking at highlighted are EPA estimates for the average of what they think was going on in 2009, but as they estimated at 3 different points in time. So in 2010, they were still using their estimates way back to the 1990s. Our study came out in 2011 and said they're off by perhaps tenfold, and the EPA responded very quickly and came out with an estimate which looks almost identical to ours, using much of the same data sources, somewhat different interpretation, but the same conclusion, more or less. However, they got heavily criticized by industry, and 2 years later, in 2013, they cut that estimate in half down to 0.88%. And the EPA, I don't think it was justified. A lot of others don't think it was justified. And the Inspector General for the U.S. Environmental Protection Agency has criticized the agency for this process or the lack of science behind that decision. We look at other methane emissions, and here I'm giving you total life cycle emissions for conventional natural gas and for shale gas. Papers listed chronologically, with ours the 4th one down there, the first to look at shale gas. All of these papers since ours that I'm showing you here came out within 8 months after our paper, so again, a very, very quick succession. And I'm not going to critique these one by one. I think ours is as good or better than any. But fundamentally, our study and all of these others are relying on an extremely limited set of data. They just are small reinterpretations of this very limited data set. I think it's more useful to put those data behind and look forward at the incredible amount of science that has been done in the last 3 years or so. One of the conclusions of our paper, again, is that the data available to us was limited and poorly documented. What we really needed is higher quality science, and I'm very pleased to say that the research community has taken up that challenge, and there's been an explosion of high quality estimates of methane emissions published in the last 2 to 3 years. This slide summarizes the studies which I think are among the best or the most noted. The top 7 ones there are upstream emissions, so again, at well sites or at gas fields, and these are all from either shale gas or other unconventional natural gas, such as pipe sands. In the middle, there are 2 recent estimates for what goes on in downstream emissions that I'll talk briefly about in a minute. And then at the bottom, there are 2 studies which talk about sort of a global average for what total emissions might be, and I'll talk a little bit about one of those as well. If we look at the top studies, the unconventional gas emissions, the upstream emissions. This is one of those studies. Anna Carlton, who was a graduate student at Purdue, working with a bunch of us on a co-author of this study. And the basis of this study is to take an airplane that's equipped with methane monitoring equipment. We flew over a shale gas area in southwestern Pennsylvania back in June of 2012. And you can see on the left that as the airplane flies with different distances away from a gas rig, marked there with an arrow and a dotted line in the middle, and goes up and down in elevation above the ground, that it encounters different quantities of methane. The hotter colors show more methane. And those data are integrated and summarized on the right, shows a clear plume of methane rising from the rig here. We're also able to get an average emissions for the field as a whole, which agreed reasonably well with what we had published in our paper 4 years ago. It's actually somewhat higher then, but within the range of what we had predicted. But the interesting thing here, the importance of individual rig fluxes. There were a number of rigs that were very strong emitters, and surprisingly, several of these were wells which were being drilled. They had not yet reached the shale, Marcellus shale in this case. They certainly had not been hydraulically fractured. They were not in production. We and several others, including the EPA, had assumed that there'd be no emission from this stage of development, and yet, in fact, there were very, very high levels of emission here. So one of many surprises that we're learning as we look more and more closely at shale gas and methane. Another recent study, this one published last fall in the AGU publication Earth's Future. In this case, Schneisinger used satellite data to measure methane concentrations from space, integrated in both space and time. And in the upper right-hand corner here, showing you from 2003 to 2012, the concentration of methane in the atmosphere over the entire planet. The top is the North Pole, the South Pole is shown there at the bottom, the equator is indicated by 0, and each latitude there in between, we're looking around the entire circumference of the Earth at the integrated methane concentration. And you can clearly see that that increased in the Northern Hemisphere after 2007 or so as the shale gas revolution took off. Lower left-hand side, we're looking in detail at the United States, period 2006 to 2008 on the left, and then 2009 to 2011. And the methane concentration has increased. This paper attributes that almost entirely to shale gas and shale oil development. They took a detailed look with their satellite imagery at the Bakken oil, shale oil fields in North Dakota, and at the Eagle Ford shale gas field in Texas. They're able to put methane emission estimates on these based on the change in atmospheric concentration they saw and the amount of development that's going on in the ground, and they found very high levels of emissions. I'll come back to it right now. This figure summarizes the various upstream methane emission estimates from shale gas and other unconventional gas that have been published since our paper came out. So our paper is up there at the top in green. The 2 estimates from EPA as to what upstream shale gas emissions might be. The estimate from 2011 is like ours, and cut in half in 2013. Then several other estimates, and the ones shown by arrows are the 2 I just been talking on. Cornell, the airplane flyover, and Schneisinger, the satellite data, and they are in good agreement with close to 10% methane emissions, very, very high. The lowest of the estimates is that of Allen et al. This is the Environmental Defense Fund organized study funded by industry and closely coordinated with industry. They came up with a number that is surprisingly low, and when I commented on this when the paper first came out, I stated it looked like a best case scenario. It was at the very low end of what we had predicted as possible from our 2011 paper. And you can imagine that since they are going only to sites where industry allows them to go, working only with operators who want to cooperate with them, and are going at times when industry expects them, that industry is doing the best they can. It may be more profitable than that of the study. This paper came out last month by Howarth and two other co-authors. Howarth is the holder of the patent on the instrument used by the Allen et al. Study, the Environmental Defense Fund study, and also the EPA studies, in fact, going back to the 90s. And in this paper, Howard says it's rather easy to misuse their instrument, which has two different types of sensors. Unless you calibrate carefully as they switch between sensors, you can get major errors, which would tend to result in underestimation of methane leakage. Whether or not that actually applies to the Allen et al. Study or the EPA studies was not addressed in this paper, but they clearly imply that there's a possibility that that would be the case. We've walked through the other studies here, the Patron et al. Study, two of them, and the Carrion et al. Studies. Those are done by the National Oceanic and Atmospheric Administration. They show reasonably high emissions. The bottom four estimates are all from one study, Cornell et al., that was published this spring again, and they show high emissions for one field and low emissions in three other cases, very low. Let me just comment on their Marcellus number, the bottom one there. That's to the northeastern Pennsylvania Marcellus shale field. The study we had with the airplane flyover in southwestern Pennsylvania, also in Marcellus, and clearly gives us a very different pattern. Both these studies use airplane flyovers, and I think they both have good methane emissions, but they are both normalized to the rate of production at the time that the measurements were taken. And we're not a state relationship here. I'll come back to that in just a second, but Peischel acknowledged that their numbers are different from the Carlson et al. Ones. They suggest that's because the northeastern Marcellus, where they are, is a dry gas, and Carlson et al. Is a wet gas, and the methane emissions might be higher in wet gas areas, more oil-producing regions, simply because industry is not as careful in capturing the gas. They're not that interested in the gas, and they might be more prone to letting it leak. But the other possibility is this non-steady state situation I just alluded to. Proceed to the next slide. Our study, the Carlson et al. Flyover, happened in 2012, and if you look at 2012 there with the arrow saying gas going down, there are 800 or 900 gas rigs in the United States drilling for shale gas at the time of our study, a lot of activity. By the time the next study came along and found much lower emissions in 2013, there were fewer than 400 gas rigs in the United States. So it's been cut by half or so. The oil production would still be high in 2013 based on the operations in 2012, but the emissions associated with that might be lower because there's less activity. So again, these are limited time studies, ours and theirs, and they are quite likely non-steady state relationships, which perhaps require greater interpretive care than many of us have given so far. I think the best study of these in terms of its robustness is the Schneising et al. It integrates several gas fields in space across the United States. It also, based on the satellite data, this is many years of data, so we're not looking at simply a non-steady state phenomenon. And it suggests somewhere around 10% of the methane from shale gas operations is emitted to the atmosphere over the lifetime of the well at the gas field. So look at the downstream emissions, what's going on in terms of storage and distribution transmission. More than half of the pipelines in the United States is 55 years old or older. It's not surprising that they leak. We know that in a qualitative sense, tons of studies, and of course there are massive explosions now and then. This one from San Bruno, California, back in 2010. There was a major explosion in Manhattan a year ago as well. So explosions happen, but smaller leaks are much more prevalent, of course. And our quantitative data on those are limited. I showed you this slide before, the Department of Energy study there at the top, and ours suggests 2.5% leakage in these downstream. EPA, using their data from the 1990s, still says it's less than 1%, about 0.9, but all of these are very rough estimates. There are new data coming out now which will help improve that situation soon. This is one that was published just a month or so ago, looking at methane emissions in the Boston metropolitan area. They attribute about 2.7% emission rate. So I won't say much more about it. It's a great study. It tends to support our estimates for a variety of reasons. On the other hand, this study came out a month or so ago as well, looking across a wider distribution of areas in the United States. They went back and resampled some of the pipeline systems, for instance, that the Environmental Protection Agency had looked at with industry back in the 1990s, and they said actually leakage has improved since then. I think this is a quality study with quality data, so it tends to support the lower estimate of EPA. So we have great uncertainty still what the downstream emissions are. On the other hand, we have a good estimate of what total methane emissions is from the entire natural gas system, full life cycle, again from well to consumer, to the time before the shale gas boom. And that's based on a study published in 2013 in Proceedings of the National Academy of Sciences. They used nationwide monitoring data from over 12,000 observational stations for the period 2007 to 2008, and then they compared this with the EPA inventory assessment using a inverse spatially explicit model. And they conclude that the EPA estimates have got to be at least twofold too low for emissions, again, before the shale gas boom, both for the natural gas industry and also for animal agriculture, by the way. So they say the emissions have to be at least 3.6 when you look at the entire natural gas operation. That compares with our estimate of 3.8. So I think our estimate of 3.8 we published 4 years ago is looking quite good for conventional gas, and the Schneising all satellite data suggested we underestimated the problem from shale gas, and it's worse than we thought. So if we take those estimates and now go back and compare the greenhouse gas footprint of shale gas and conventional gas with diesel and coal, this is my latest assessment, grams of carbon dioxide equivalents per megajoule of energy expressed as grams of carbon. And the yellow here are the direct and indirect carbon dioxide emissions. In that regard, natural gas and shale gas look good, but the red are the methane emissions converted to carbon dioxide equivalents, in this case using a 20-year time period from the Intergovernmental Panel on Climate Change 2013. The shale gas estimate for methane emissions here is based on those satellite data from Schneising et al., and including a 2.5 downstream methane emissions. And the conventional natural gases and all of the others are based on our study from 2011. Our estimates for oil and coal are very similar to those for EPA, by the way. So using these estimates and showing a 95% confidence limit there with the bars, I would conclude that shale gas is a disastrous fuel from a climate standpoint, and the conventional natural gas is also far worse than diesel or coal. Showing you here based on the fuel used just to generate heat. Now, the specific use of the fuel makes a difference in how we do the comparison, and I'll show you that briefly here. We have a paper submitted which goes into this in much more detail, but I have a relatively short time with you today, so I'm going to keep this short and simple. The bar graph on the left has an upper part and a lower part. The top part is for generating electricity, the lower part's for home water heating. And for each of those, we're showing different methane emissions from the various studies. So Schneising et al. Is the satellite imagery for shale gas. The top number is our estimate for conventional natural gas. Other estimates are in between. We're comparing natural gas with coal in terms of its greenhouse gas consequences here, with natural gas being worse than coal if you're to the right of that bar associated with the number 1 at the bottom. So in all of these methane emission estimates for generating electricity, natural gas is worse than coal in terms of its greenhouse gas consequences, or or comparable to. For the Schneisen shale gas one, it's more than twice as bad. Shale gas is twice as bad as coal in terms of generating electricity. The situation is worse when we look at home heating. In this case, home water heating would be a similar case for space heating, I believe. What we're comparing here is the use of natural gas in home for conventional hot water heater, the way that 80% of American homes do. Hot water heater in your basement with natural gas plumbed into it. And we're comparing that with hot water generated from a air source heat pump in your basement that's powered by electricity, with that electricity coming from coal. So again, any of the bars to the right of that one line mean that the footprint is worse for natural gas than for coal, and in all cases, it's far worse. It's often twice as bad a greenhouse gas footprint, 4 times as bad a greenhouse gas footprint if we use the Schneisen estimates to use natural gas in your home to heat water as opposed to using coal-generated electricity and a heat pump. So, I don't think natural gas is a bridge fuel. It has a very large greenhouse gas footprint. Conventional natural gas is bad, but shale gas, which is increasingly becoming the source of natural gas in the United States, is worse, and that's well captured in this cartoon that came out in the Washington Post back in January. If you look at the lower right-hand corner, I left a little, but people can't see it. Methane's an invisible gas, but it's insidious. It leaks, and it undercuts the argument that fossil fuels can be used in any sort of bridging to the future. If shale gas is a bridge to nowhere, then what should our energy future be? And I'm a big fan of Mark Jacobson's analysis. I'm sorry I didn't hear him earlier, but I'm proud to say that I've worked with Mark on 2 published papers. One came out 2 years ago, laying out a blueprint for the state of New York to be fossil fuel free largely by 2030, and one that came out last year for California. You heard the details of these earlier today. I won't go into them, other to say that I'm a big believer that we not only can do that now, but that we have to do it now if we take climate warming seriously. And at a personal level, I have taken this seriously. That's my house in upstate New York. We had several days where it was well below 0 Fahrenheit this past winter. Our house is carbon neutral. It's heated entirely with a ground source heat pump, so-called geothermal heating. That's powered by electricity. We produce half of our own electricity with PV solar, and we buy the other half certified wind power. So our house is carbon neutral. Our water comes from an air source heat pump of the sort I described, and we have a Nissan Leaf, which we use for half of our total driving. So again, I appreciate the opportunity to talk to you today. I'm sorry I can't be there in person. I'd like to acknowledge the individuals on the left who've been very helpful in the work I'm describing today, and also I'm grateful for the funding sources, largely from Cornell University, but also from the Clark Foundation and the Wallace Global Fund. Thank you for your time.
Fantastic. Any questions?
The question for the group is the CDC using data points as inputs into their analysis on time-dependent value.
No, because time dependent is based on the cost of the fuel.
Correct. How convenient.
All right, we have a call-in user. I'm going to unmute. I'm not sure if that's you, Bob, but I'm going to unmute you real quick. Bob, can you hear me? Nope. I guess he was not able to get in, unfortunately. But we do have his contact information. If anybody has any follow-up questions to him, feel free to shoot it to any one of us, and we'll make sure that he gets it. If not, I know his information was up there as well, that you can get in touch with him. So with that, if everybody wants to stand up and do 5 jumping jacks real quick, get the blood flowing a little bit, and then we will move right into to the Honda house with Michael Koenig.